Good morning all. We are discussing about magnetic torque. This is the second class on magnetic torque. In the first class, we have seen what happens when you suspend a rectangular coil carrying current in a uniform magnetic field where the plane of the coil is parallel to the magnetic field. Now consider the second case. What happens when the plane of the coil is oriented in any direction? As in the previous case, consider a rectangular loop PQRS having length L and breadth B, which carries a constant current I. The rectangular loop PQRS is placed in a magnetic field B. Note that the length of the loop is L and the breadth is B. The loop is placed in a uniform magnetic field B. As in the case of the previous problem, we will find out what is the force on each arm. To find out that, we are going to define a parameter called theta. What is theta? Theta is the angle between normal to the plane of the loop, that is represented in the figure by the vector n, and the direction of the field B. N is the vector that is normal to the plane of the loop. Because the plane of the coil is oriented in some direction, you can have a vector n which is normal to the plane of the loop. Then the angle made by the magnetic field and the vector n is called theta. Let us evaluate what is the force on the arm PS. The force on the arm PS, let it be F3. We can represent it as I into dl3 cross B, where dl3 is the small element on the segment PS, and we can represent that integral as I into integral dl3b sine 90 minus theta. Why it is sine 90 minus theta? Because the angle between dl3 and b is 90 minus theta. You can see it from the figure. Theta is the angle between n and the magnetic field B. Therefore, the magnetic field B and the line segment dl, that is 90 minus theta, and sine 90 minus theta is cos theta. Therefore, F3 is IB cos theta into integral dl3. Now, what is integral dl3? If you integrate a small element, then you will get the distance PS. PS is actually the breadth of the coil. Therefore, integral dl3 is nothing but the breadth of the coil. Hence, F3 can be written as IB B cos theta, where B is the breadth of the coil. Now, let us evaluate the force on the arm RQ. Let it be F1, that we can represent it as I into dl1 cross B. As in the case of the force on the arm PS, here the force on the arm RQ can be represented as IB cos theta into integral dl1, where dl1 is the small element of length in the segment RQ. If you integrate dl1, again you will get B, which is the breadth of the coil. Therefore, the force on the arm RQ can be represented as IBB cos theta. Now, if you observe, the forces F1 and F3 are equal in magnitude, but they are opposite in direction. The forces F1 and F3 are equal in magnitude, but opposite in direction and have the same line of action. When two forces which are equal in magnitude and opposite in direction and they have the same line of action, then the resultant will be 0. Hence, the resultant of F1 and F3, or the resultant effect of F1 and F3 on the current carrying loop is 0. Now let us find out what is the force on the arm. QP. Let it be F2. We can represent it as I into integral dl2 cross B, where dl2 is the small element of length along QP. The magnitude of the force can be represented as I integral dl2B sine theta. Here, the angle between B and dl2 is 90 degree. F2 equal to I into integral dl2B sine 90. It is because the angle between dl2 and B is 90 degree, which is evident from the figure. Hence, F2 can be represented as F2 is equal to IB into integral dl2. Now, what is integral dl2? If we integrate a small element dl, then you will get the length of the segment QP, which is nothing but the length of the coil. Hence, integral dl2 equal to L is the length of the coil. Hence, F2 becomes IBL. In the same way, we can calculate the force on the arm SR. Let it be F4. Now, F4, which is equal to I into integral dl4 cross B, where dl4 is the small element of length along SR. Now, the magnitude of the force F4 equal to I integral dl4B sine 90, because the angle between dl4 and B is 90 degree. The length of the coil is perpendicular to the field. Now again, this will becomes IB into integral dl4. Integral dl4 is again the length of the coil. Therefore, the magnitude of the force on the arm SR F4, that is equal to IBL. Now, from the direction of the current and from the direction of the magnetic field, we can conclude that F2 acts perpendicular to the plane of the paper and outwards, whereas F4 acts perpendicular to the plane of the paper and inwards. Just look the direction of the current and the direction of the magnetic field, and we can find out the direction of the force. And F2, which is perpendicular to the plane of the paper and directed outwards, and F4 is pointing inwards to the paper. That is, even though F2 and F4 are equal in magnitude, their line of action is different. One is pointing inwards and one is pointing outwards. The forces F2 and F4 are equal in magnitude but opposite in direction and have different line of action. When two forces are equal in magnitude, opposite in direction, but they have different line of action, what is the result? They will constitute a couple, and as a result, the coil will rotate. F2 and F4 are equal in magnitude, opposite in direction, and have different line of action, so they constitute a couple. Now, let us evaluate the torque acting on the coil. To find the torque acting on the coil, go through the second figure. In the figure, you can see two forces acting, F2 and F4, and the perpendicular distance is given by B sine theta. The general expression for the torque is the torque acting on the coil, which is nothing but one of the forces into perpendicular distance. Here, one of the force, the magnitude of the force is IBL, and the perpendicular distance is nothing but B sine theta. Go through the figure and you will see the perpendicular distance is B sine theta. Now we can rearrange it in the following way: tau is equal to IB, then LB sine theta. If L is the length of the coil, B is the breadth of the coil, then L into B, that is length into breadth, is nothing but the area of the coil. So the torque becomes IB A sine theta, where A is the area of the coil or area of the loop. Suppose the coil PQRS has n turns, then the torque acting on the coil, tau, is given by n IBA sine theta. The torque tau is equal to n IAB sine theta. Now let us simplify the expression. You take I into A as M, which is nothing but the magnetic moment of the current loop. Take M is equal to I into A, which is nothing but the magnetic moment of the current loop. And you assume that there is only single turn, that is capital N equal to 1. Then the expression for torque becomes MB sine theta. Because Ia is equal to M and N equal to 1, therefore torque tau is equal to MB sine theta, or torque tau can be represented as M cross B.